Well, hi there, boys and girls. Today we're going to have some practice answering that second question that this chapter is devoted to. And that question, of course, is, if I have a convergent series, can I figure out what it converges to? And so let's just get some practice here. I've got a sum here, an infinite sum, and let's take a look at this general term. I've got an exponential over a factorial, so I'm fairly convinced that this is going to converge. Of course, I could do the ratio test to prove it, but it is a convergent series. So let's see if we can figure out what it converges to. There are three series that you are just supposed to know, and one of them is a series for e to the x, and it is x to the n over n factorial, and this series will converge for values in between negative infinity and positive infinity. This series is a very nice series, and it equals e to the x. So all we have to do is recognize, hey, I've got an exponential on the top, and the x has been replaced with a 3. It's 3 to the n over n factorial. So since I see exponential over a factorial, they're all positives, this is going to be the summation of 3 to the n over n factorial, starting from 0 and going to infinity. This is going to equal, my dog just sneezed, that's funny. This is going to equal e to the third. The x has been replaced with the 3, so this is e cubed. Whatever 2.71828 to the third power is going to be that. We're just going to call it e cubed for now. Let's take a look at another one. Here is an alternating series, and I've got factorials, and I have 2 to the 2n plus 1 is my general term. Now, if it's alternating with the 2n plus 1 factorial, there's another one you're supposed to know, and that one is sine of x, the series for sine of x, which is starting from 0, going to infinity, alternating, and we have odd powers of x. X to the 2n plus 1 over 2n plus 1 factorial. This is going to equal sine of x, and you need to know this. So let's take a look at this general term. I've got an alternating series, 2 to the 2n plus 1 over 2n plus 1 factorial, starting from 0 to infinity. That's what this series is. So if you know what sine of x looks like, what has been replaced with the x? Oh, and by the way, this series over here is valid for all real numbers. So the x has been replaced with a 2, therefore this series will converge to the sine of 2. Now this third example is a convergent series. I know it's convergent because it's alternating. The terms are approaching 0 and they are decreasing in magnitude. This is an alternating series which will converge. And on top of that, it's geometric. It is a ratio to the n power. And remember, if you have a ratio being raised to the n power, as long as the absolute value of that ratio is less than 1, it's going to converge. And on top of that, you've got this nifty little formula to what it converges to. The sum is going to be the first term over 1 minus the common ratio. So here I have a geometric series. We're doing times negative 2/3, times negative 2/3, times negative 2/3. So my sum is going to equal the first term over 1 minus my common ratio, which is negative 2/3. So that's going to equal 1 over 1 plus 2/3, which is going to be 5/3, which is going to equal 3/5. All right, so let's take a look at a theorem here. This theorem says, I'm going to let you can read this. This theorem says if you have a function that's just a power series and you've got some radius of convergence, it tells you how to take the derivative and the integral. The derivative would be just the derivative of each term one by one. The derivative of a sub 0 is 0. The derivative of a sub 1 times x minus c is a sub 1. You're just taking the derivatives term by term. Even this last, the general term, take the derivative of that, you bring the n down, and then subtract 1 from that. So this is just saying you have the right to take a derivative. You can also integrate term by term by adding 1 to the exponent and dividing by that. This theorem says that if you do this, the radius of convergence is not going to change. However, the interval of convergence might. We might pick up an endpoint or we might lose an endpoint whenever we do this. So let's take a look at how we're going to work these problems. I've got a function defined by 1 over 1 minus x, and I know that that is a geometric series. My r is equal to x. We did this one in class already. So the first 4 terms are 1, and then plus x, and then plus x squared, and then plus x cubed. we've written this. There's the first four terms, and then all the way out to the general term is x to the n. So there's answering the first part of it. Now, for what values of x does this series converge? We already know that a geometric series, the ratio has to be between -1 and 1, and a geometric series will never ever converge at the endpoints. So now it says use your answer to A to find the Maclaurin series for f prime of x. So we're supposed to practice taking a derivative here. So my f prime of x is going to equal, take the derivatives of all these terms, and we need four non-zero terms. Now when I take the derivative of 1, I get 0, so I don't get to count that as a term. When I take the derivative of x, it's a 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared, and that's only 1, 2, 3 non-zero terms. So the next term would have been x to the fourth, and when you take the derivative of that, you get 4x cubed. Now we also have to write the general term. The general term is the derivative of x to the n, which is going to be n times x to the n minus 1. Now I'm going to tell you that whenever you take the derivative of a series, you are never ever going to pick up an endpoint. So this series converges between -1 and 1. Now why did we do that? Well, now we're going to practice finding derivatives and integrals to find new functions to figure out what series converge to. So here we have a series that doesn't match anything I've done before. It's not geometric because it's not like times 1/3 times 1/3. It's also not a e to the x or a sine of x or cosine x. However, it says use your answer to B to find the sum of the infinite series. Now in B, we got that f prime of x was summation of n times x to the n minus 1, and this one would actually start at 1, going to infinity. So, how does this series look like that? Let's take a look at the general term. How does this look like it? That general term is n over 3 to the n minus 1. Now we could rewrite that as summation of 1/3 to the n minus 1 times n. This 3 to the n minus 1 in the bottom can come up to the top as a 1/3. Alright, so how is this going to help us? Well, I know that my original function was 1 over 1 minus x. This series right here was the derivative of that. That means that my series here represents a function of x. So if we write this as 1 minus x to the -1, I can actually take the derivative of that, which would be -1 times 1 minus x to the -2 times the chain rule times -1, so that turns that into a +1, which is 1 over 1 minus x squared. That's the function of x that this series represents and converges to as long as we're plugging in values between -1 and 1. So this means that my series, n times 1/3 to the n minus 1, I'm just going to replace this x with a 1/3, so this is going to equal 1 over, now 1 minus 1/3 is 2/3, and 2/3 squared is 4/9, and we flip that over and we get 9/4. The sum of this infinite series equals 9 over 4. Alright, now we're going to do an integral. And it says use your answer from A to find the Maclaurin series for the integral from 0 to x of f of t dt. So I'm going to do the integral from 0 to x of f of t dt, which just means replace all of those x's with t's, which is going to give me 1 plus t squared plus t cubed plus ... all the way out to the general term of t to the n dt. And we're just going to integrate this term by term, so the integral of 1 with respect to t is t. The integral of t is 1/2 t squared. And the integral of t squared is t cubed over 3. And the integral of t to the third is t to the fourth over 4. Now let's integrate the general term. We add 1 to the exponent, so that's t to the n plus 1. And we divide by that, divide by n plus 1. And we're going to evaluate this definite integral between 0 and x. So we're going to plug in an x for all our t's, so we'll get x plus x squared over 2, no factorials here, plus x cubed over 3 plus x to the fourth over 4 plus ... x to the n plus 1 over n plus 1, and then minus plug in 0. So if I plug in 0 for all of those t's, I'm going to get a bunch of zeros. So that's not really going to affect anything. 0. So here is the first 4 terms and the general term for the integral from 0 to x of f of t dt. Now, whenever you integrate something, you integrate a series, you're going to have to check the endpoints. Earlier, we knew that this is valid for -1 is less than x is less than 1. Let's check x equals 1. So I'm going to plug 1 into this general term, which that will give me the series of 1 to the n plus 1 over n plus 1, which is 1 over 1 plus, and I think that's starting at 0 so that we can have an x there. X to the 1 over 1, yes. So 1 over 1 plus 1 over 2 plus 1 over 3, that is a divergent series. We know that's the harmonic series that diverges. But what about checking x equals -1? If we plug in a -1 for that x, I'm going to get -1 to the n plus 1 over n plus 1, which is going to be, we're starting this at 0, going to infinity, that's going to be -1 over 1 plus 1/2 minus 1/3 plus 1/4, which is an alternating series. The terms are getting smaller in magnitude and they're also approaching 0. That means that my interval of convergence, I have picked up an endpoint. -1 is okay to use. Alright, so let's use this to figure out the sum of the infinite series. This is our series right here with, again, x has been replaced with a 1/3. So we have the series of 1/3 to the n plus 1 over n plus 1. Again, we can take this 1/3, 1 over 3 to n plus 1 to the top. So that represents the sum of this infinite series. X has been replaced with 1/3. So all I have to figure out is what is my integral. Now f of x was 1 over x minus, or sorry, 1 over 1 minus x. What is the integral of 1 over 1 minus x? Well, it's almost a natural log. We're just missing a negative, so it's negative natural log of the absolute value of 1 minus x plus c. That means that this series equals negative natural log of 1 minus x as long as x is in between -1 and 1, and my x is 1/3. So the sum of this infinite series is going to equal negative natural log of 1 minus 1/3, which is 2/3, which you could also write this as the natural log of 3/2, because we can take this negative up there as an exponent and flip it over. So anyway, we're going to practice this tomorrow in class, and I will see you guys then.